So let me present my screen. Yes, blank screen. Okay, so don't worry. What I meant was, okay, so we'll continue from the where we left off. Okay, so just a minute to have a connectivity. I'll just go to the point where we left off. Yeah, right. Yes, okay. Yeah, just to see this equation, everyone. Yeah, this is like some verse in Quran, some verse in Bible, or some poem in Bhagavad Gita. Okay, so for statistical physics, this is like that. Okay, it's a powerful equation which describes about the system in terms of the probability distribution. Okay, so this could be used for every case, and then we can derive information about the system. Okay, so that's why I was saying it is very, very powerful expression. Okay, so in this powerful expression in the denominator, what you see is in the denominator, what you see is a partition function. So this is a partition function which takes care of or expresses all the accessible states and lists down all the accessible states for a given system and calculates its probability, sums those probability and puts in the denominator. Okay, right? So we would be using this quantity or this expression and most of the cases. Okay, so as per the discussion today, we are supposed to have a discussion on systems being existing in equilibrium. That is one thing we want to discuss. Another thing was, if things are exist in equilibrium, is there any way we can express or describe that equilibrium systems using a simplest method, which is Gibbs principle? Okay, so in a way, if this expression, whatever you see, could be converted for a equilibrium situation, so in that way what happens, this expression itself becomes a Gibbs principle. Okay, so that is the power of this expression. Now we will just take a simplest scenario and we'll describe that. Okay, right? So let me start. Okay, so I'm talking about the equilibrium situation. So to describe the equilibrium situation in statistical physics, there is something called equipartition theorem. Okay, equipartition, okay, theorem, right? So students can get away with this, not bothering about this, not bothering about it. But as a teachers, we should know about it. Okay, because it is going to be useful in understanding the quantum physics. Okay, what is this theorem says is, I'll go very, very slow because a lot of mathematics is there. It says earlier we found a mean value of any energy system, right? So there are so many internal microscopic systems or microscopic entities are there in a large macroscopic system, and we found what is the possible energy of any one of them, a given microscopic system in it. So that was the mean energy, right? So likewise, equipartition theorem says the mean value of each independent, okay, mean value each independent quadratic quadratic term in the energy is equal to okay, half k T, where K is a Boltzmann constant. I'll tell you what I mean. I'll tell you. Okay, let's get back and find out. Okay, let's just take a simple situation. Okay, let's take a nucleus. Electron is revolving around the nucleus. Okay, what is this? It is just equivalent to a spring mass system. Okay, sorry, it's a pendulum system, or it is equivalent to a spring mass system. What is a spring mass system? A spring is there attached to a mass. The spring is having some spring constant. Let me say spring constant Ks, and there is a mass. Okay, so frictionless stable. I'm just taking a classical analogy. Okay, now if you just give a small displacement to this mass, what happens? The spring, because of the spring, this mass makes an oscillation between back and forth. Okay, oscillations. Okay, very good. We know that. Now, if I had to write down the energy of this particular spring mass system, or a spring, or a pendulum, simple pendulum, okay, you see, I am relating a classical scenario to a quantum scenario, because even in a quantum scenario I see the oscillations. Okay, right? So here, if I have to write down the total energy of the system, E is equal to half mv square, which is a kinetic energy of this particular mass, plus the spring constant half k. If it is moving, I'll just write down x square. Okay, with the positive movement. So half kx square is a potential energy. This is a potential energy, and this is a kinetic energy. Okay, and you can ask me, how did you get this half kx square as a potential energy? Of course, you can derive that. How? See, when you stretch it, it induces a restoring force onto the system. What is the restoring force? Minus k s x. This is a restoring force, which is equal to, okay, rate of change of the potential. Let's call the potential is some u. Du by dx is the rate of change of potential. By the way, the rate is changing in such a way, it always opposes the change in the system. So there is a minus sign there. There is a minus sign left and right, cancels. Du is equal to ks into x into dx. Now there is a derivative on the left and right, so I'll integrate. So u would become half k x square. That is what I have written, a potential energy of a spring mass system. This would even this would be even applicable in simple pendulum. In the simple pendulum, you don't see any spring, right? So what is the equivalent spring constant here? So here the kinetic energy of the system is half m omega square x square. What is the omega? Omega is angular frequency of the oscillation. Okay. So by the way, if you want a spring constant in a simple pendulum situation, which is simply equal to, okay, square root of m is, okay, omega square is, okay. So okay, let me write down neatly. So in place of k, I have m omega square. What is omega? Omega is square root of k by m, or a spring constant. So just to avoid the confusion, okay, ks, right? Write down neatly, spring constant divided by mass of the system. Okay, so now I know energy of a spring mass system in terms of kinetic energy, in terms of potential energy, I know. Similarly, if I just take a microscopic system, this is a microscopic system which is showing some oscillations just like a simple pendulum or spring mass system. It is going to have some quadratic contributions coming from its velocity, coming from its potential energy. Okay, so if I take a collection of many microscopic systems, each one is going to have such energy contribution coming into the overall energy. Okay, so now what we will do, okay, so equipartition theorem is saying, if there is any term with a quadratic contribution coming, here you see there is a quadratic contribution coming from v square, contribution coming from x square. Equipartition theorem is saying, if there is any term of quadratic contribution, its energy is going to be equal to half kT in the I'm sorry, mean energy contribution. Okay, now there are, for any given atom, even given oscillation, there are two contributions coming from velocity as well as position. So in terms of quantum mechanical system, what I will do, I will just take the energy, I multiply and divide by m, okay, and I will just replace x with a q, position operator or position. So m into v is the momentum. What I'll have, p square by 2m plus kx q square by 2. Okay, so this is the energy contributed by any given quantum microscopic system. Let's say, okay, I'll put a micro. Let's say I have n such systems taken, n systems, or you can say microscopic systems. Okay, let's say I have n microscopic systems. Now usually what I do, each one would contribute, or each one is described by, okay, overall energy is, each one is described by its position vector and momentum vector. How many such things? Qn will be there, Pn will be there. Okay, now what would be the total energy? Total energy is energy coming from each one of them, like that, whatever I described here at the top. Okay, very good. Now for simplicity, what I will do, I will just take the energy. Let me pick one particular element or particular microscopic system which I like. Let's say I like the one with the index I, okay, right, whose contribution of qi and pi I know. Okay, right, let's say I know pi contribution coming from that, and I would say I don't know any other contribution coming from that guy, so I'll just incorporate in the overall equation. So what I'm doing, I'm just keeping everything else into that. Okay, you see, this is what I did. So that the one which is contributing from quadratic term, okay, what I mean is EIPI is a quadratic term, just like at the top. What is this? P square by 2m. Na? So let me write down that as some B into Pi square. Okay, so only that particular single term I taken it out, and every other terms I'm keeping in the expression. This time I call that expression is some E prime, which is slightly different from the overall E which I have taken. Why I have done that, you will see in the, as we go through the derivation. Okay, now I want to know what is such a contribution, mean value. So there are so many n particles, right? So this is a quadratic term. What is its contribution? And each microsystem is contributing such a term with a quadratic contribution. So on an average, what would be the contribution from all of them, right? On an average, some of them will contribute, let's say, something. Some of them will contribute, let's say, something. Let's say usually we collect the donations for doing some festival, let's say Ganesh Chaturthi or something. Somebody contributes 1,000, somebody contributes 500. Okay, so I just want to know what is the average, right? So I'll just take all of them and submit and divide it by overall. So here, luckily for me, there is a probability distribution. Using the probability distribution, I can find what would be the average. How do I do? Earlier I did finding a mean energy as using take the probability distribution, okay, multiply with the mean energy, what is coming from, integrate from dq to dqn, okay, dp1 to dpn, okay, right, and divided by exponential minus beta e dq1 to dqn dp1 to dpn. Okay, remember I have not separated this energy yet. Now I will do. What I will do, in place of e, I will substitute the first term and the second term without any first term coming into the picture. So what I will do, I will do that now. Okay, so E of I is equal to, please see carefully what I am doing. Okay, so summation over, I'm sorry, there is a summation at integration over, not summation, integration over exponential b. Okay, I'm missing so many things. Minus, I'm missing. Minus, in place of E, I should put EI plus E prime. Very good. EI dq1 to dqn dp1 to dpn. Okay, divided by, I will do the same thing with the denominator as well. Okay, exponential minus beta ei plus e prime dq1 to dqn dp1 to dpn. Okay, now if you see carefully in the numerator and denominator, only difference is in the numerator I have extra term ei, because I am trying to find the average energy of EIs, right, coming from each individual case. Okay, so what I will do, I have a freedom to, these are like multiple integrals. You see how many integrals are there? Each term is contributing one integral from the Q's. Each term from P is I'm contributing, like there are n integrals. So it's actually 2n integrals. Okay. So what I'll do, I can separate. How do I separate? Let's say I'll separate exponential of minus beta ei. Okay. So ei, right? And there is a ei depends on only pi. It is doesn't depends on anything else. So I can just put it outside. So I'll have minus beta into e prime. Okay, e prime dq1 to dqn. Now you see carefully, dp1 to dpi minus 1 dpi plus 1 dpn divided by, okay, summation over beta into ei dp, sorry, no ei in the denominator, dpi summation over beta e prime, okay, dq1 dqn dp1 to dp minus 1 dpi plus 1 up to dpn. Now you see the integrands, second integrands in the numerator and denominator are same, so they just cancel. They just cancel. What I am left with? The energy, mean energy of EI is summation over beta EI dPi summation over beta EI dPi. Okay. Now, if you carefully look at this term, what I can do? I can convert this to minus derivative of derivative with respect to beta integration over beta EI dPi. I can do that. So, you take the derivative with respect to beta, I will get extra EI term inside. So, the entire numerator is converted into just whatever is the denominator derivative. You see? So, denominator derivative is there in the numerator. Okay? So, which means, again, I will play the same trick which I was playing earlier yesterday. What we can do, we can say this, the entire term, entire expression is derivative of log of, you see, okay, log of integration, okay, integration of exponential minus beta EI dPi, okay, right? So this is what I have. Now let's find out what is this integrand. Integration of minus beta EI dPi. By the way, earlier EI is, we assume, which is equal to, okay, we assume which is equal to B into Y, sorry, B into Pi square. So energy is just a quadratic term, B into Pi square, which implies integration of beta B Pi whole square dPi. This is the integration I want to find. Okay, now the kinetic energy can become from minus infinity to plus infinity. So is the momentum. So momentum goes from minus infinity to plus infinity. Okay, right? This is the expression I want to find out. What is the value? Now, if you carefully see this expression, okay. So what you can do is, let's assume, okay, y equal to square root of beta into Pi. If you do that, so what happens? This integrand becomes, what happens if integrand? Integrand becomes, when I just take a dy, which is dpi. So dpi is 1 by square root of beta dy. Okay. So if you substitute those things, remember, the integrands are not going to integral values are not going to change, because it is just minus infinity to infinity. I'm just scaling with the square root of b. That's all. Okay. So I can just have the same integral limits. Okay. Minus exponential beta into y square. Beta into y square dy by square root of beta. Let's put the square root of beta outside. So what I left with? Integration minus infinity to infinity exponential minus by square into dy. Okay, if you carefully look at this, this is a Gaussian integral. It's a Gaussian integral. In fact, you can find the value of this Gaussian integral, which is actually equal to square root of pi into b. Okay, right? Square root of pi into b you can find. Okay, so as a supporting material, I have added for the lecture notes. You can check that. So let me put this straight away. Square root of b into square root of pi by b. This is what I have. Now this is what I have. Okay, in place of the log of beta into xei into dpi. Now I want to know what is the energy. Average energy. Average energy is minus dou b dou derivative with respect to b, okay, log of this integrand. So now I found the what is the value of the integrand. Integrand is 1 by beta pi by, okay, this is what I found. Now let me find out, right? So you just expand, by expanding. What you see here is, okay, minus dou by dou beta log of beta to the power of minus half, okay, into some constant. Let me put some constant, okay. So this is what, so log a into b is log minus dou beta log beta minus half plus log c, okay. Now when you derivate a constant with any variable, that is not going to contribute. What is I left with? Only the first term contributing, so it will have minus of minus, okay, derivative of log b, okay. So which is equal to half, right? Half into derivative of log b is 1 by b into 1. By the way, what is b? B is a Boltzmann constant. So beta is kt divided 1 by kt. Beta is 1 by kt. I'll have half in the denominator. So what I have proved, in average energy coming from any quadratic term of any oscillator, which is going to be half into k into t. Beautiful. Okay. Now this is the only one term. Okay. So if there are multiple terms coming from, let's say momentum operator is, okay, there is a momentum operator coming from x component, coming from y component, coming from z component, 3 dimensions. In that case, what happens? The overall kinetic energy, this one contributes half kT, this one contributes half kT, and this one contributes half kT. Overall, I'll have 3 by kT contribution coming from these quadratic terms. Okay. Now, let's see. We are talking about a quantum system, okay, a quantum microscopic system in terms of classical system. Okay. So now we need to bring them together and try to assess the situation. Okay. Now, how do I assess the situation is, okay, let's say you just take a nucleus, there are orbits around, okay. As you go further and further, you see orbits are very close. So basically you just take a snapshot of it. When you just plot it somewhere, what you see is the initial levels are very far, okay. Initial separation is very far, okay. Later on, if you go, the levels are very close, okay. Now, so when the temperature of the system is absolutely low, temperature is low, T is low, there is a chance electrons can be found in the lowest levels, okay, where the separation between the any next two levels, okay, right, is something, let's say, which is K into T separation, like a thermal temperature, okay. So at a very low temperature, K2 is very small. So electrons cannot go out, as KT is much smaller than delta E's. Okay. In that case, okay, so electron cannot go out of the system or cannot go to the higher orbits. So the system behaves like a quantum. Okay, that is where we see qubits. That is the most important, having a very low temperature. Let's say if the T is high, in that case, what happens? Okay, so you are actually, the electron is pushed to the higher levels. Okay, now let me draw those cases. Okay, now electron is pushed to the higher levels. This time, this volume, sorry, energy, thermal energy separation is very large. So energy separation between next levels is much smaller. So delta E is much smaller than kT. What happens? The electrons are pushed to the higher order. So there is no discreteness anymore. Systems behaves like classical, macroscopic, macroscopic. Okay, so that is the importance of this temperature being very low for quantum mechanical system or a quantum computing system required. Even the even the equipartition theorem says that, because each quadratic term actually depends on half kT. Okay, so the energy of the system is of the order of kT. So that kT is very important to deal with the electron, to confine it to a quantum level or push it to the higher level. Okay, right? So as you know, you can do a classical harmonic oscillator. Even for the classical harmonic oscillator, you can derive the overall energy is simply half kT plus half kT is equal to kT. Why I'm saying? Because for a classical harmonic oscillator, if you just see classical harmonic oscillator means a spring mass system. For a spring mass system, as you can see, overall energy is simply p square by 2m plus half spring constant k square, or you can say p square by 2m plus half m omega square x square. Okay, so there is a quadratic term on the left, there is a quadratic term on the right, two terms. So what is the overall mean energy would be? Half kT plus half kT, which is simply kT. Okay, so this is a classical limit for you. Classical limit. Now, what is a quantum limit? As you know, the quantum limit means electron being confined to outermost any orbits starting from n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. So you can use quantum harmonic oscillator expression, okay, where energies are Hamiltonian. Let me write now Hamiltonian. In terms of energy, I'll write a Hamiltonian, which is momentum operator square plus half m omega square q operator square. This is a correct total energy at the Hamiltonian of the system. I'll say Hamiltonian. Doesn't matter. Okay, Hamiltonian. So here there is a quadratic term. There is a quadratic term. Probably it is something like kT. But the thing is, for the harmonic oscillator, you can do harmonic oscillator in like description. Okay, I think we will cover sometime later. Let me give you the, we will solve eigenvalue equation. Let me write not in the Dirac notation. Eigenvalue solution. Okay, maybe Dirac notation. Easier that way. So Dirac notation. In the Dirac notation, if you solve the Schrodinger equation, okay, and you can find the energies of the system, yes, n plus half h omega, where n is an integral number starting from 0, where n is equal to 0, okay, what we will get? Half h omega. This is called a 0-point energy. Okay, even we can derive this using this equipartition theorem or using Gibbs principle. We can derive this. Okay, we'll come to that. Now what we'll do, let's try to derive what is the mean energy from this particular expression of E. Okay, now we know an overall energy of the system. Now let's try to derive the mean energy of such system in a large macroscopic system. What I mean is, there is one atom, there are so many atoms like this. Okay, in that case, how do I derive overall energy? Okay, so as you guys know, what we'll do, we'll just use a probability distribution, which is, okay, exponential minus beta e divided by, okay, so let's say it's a discrete system. I can't use any integration anymore. I have to use a summation. Okay, summation over energy into exponential minus beta en, where n runs from different systems. Okay, so please don't get confused with energy runs from okay, like you can also think that, let's say there is one atom where electron is in the particular orbit n, another atom electron is in another orbit n. So likewise, I have for every corresponding n, there is an energy contribution coming from there. Okay, now you see the denominator, which is a partition function z, okay, summation over n exponential minus beta en. Okay, so what I'll do, I'll just take z for time being. Let me describe what is z would be minus beta into, okay, what is en? En is n plus half, okay, n plus half, okay, h omega, right? I'll go very slow at this point. It's slightly tricky. So which is, I will have exponential n e to the power of minus beta n h omega exponential minus beta h omega divided by 2. Okay, there are two terms. I have it now here. If you see, the second term is independent of n. I can just bring it outside. Minus beta h omega by 2. And whatever n is there, I'll have it inside. Okay. Now, if you carefully see this nth term, what I have, exponential, okay, let me do it neatly. What I have, exponential minus beta h cross omega by 2, summation over n minus beta h omega whole to the power of n. This is just like, this term is like some term x. Okay, so if we have summation of x, if you just take this, what is this? This is 1 by 1 minus x. Okay, so this is the summation rules. Now 1 minus 1, okay, so what I'll have here, which is equal to exponential minus beta h omega by 2, 1 by 1 minus exponential minus beta h omega, right? Okay, now what I'll do, okay, z I have, I can also find now log of z, which is required for later case. So if I do that, so there is one term here, there is another term. Log a into b is log a plus log b. So log of this term, there is exponential, so I'll get simply beta minus beta. This is the first term, and second term is, this is the denominator, so I'll have a minus sign, log of 1 minus exponential minus beta h omega. Okay, now I need to know the derivative of the log z also, right, with respect to beta, to find the mean energy. So I'll just preparing myself for that. So derivative of this first term is simply h omega by 2. Okay, with the minus sign, by the way. Okay, so minus of minus. So minus coming from the before the derivative, right? So next derivative of this quantity, which is 1 by 1 minus exponential minus beta h omega, okay, exponential beta minus h omega into h omega. Okay, so the minuses signs goes inside, I'll become pluses 1 by exponential minus beta h omega 1 minus exponential minus beta h omega into h omega, or you can take h omega common if you want. Okay, let me do that. H omega half plus, okay, half plus. Now in the numerator I have something which is I can send it to the denominator. It becomes beta h omega minus 1. You see how simple it has become. Now I can talk about various scenarios. Okay, this is dB by ln z. Okay, so dB by ln z. Okay, by the way, the average energy is actually somewhere I have derived. You see, where is that? Okay, let me explain directly. So the average energy is simply minus dou B log z. That's all. This is the average energy. But I just found in the top, what is that? Minus derivative with respect to B log z, we just derivative. So average energy is simply h omega 1 by 2 plus exponential beta h omega minus 1. Now let's do the discussion. What is the discussion? Discussion is, let's say temperature is very, very high. Let's say T is high. In the T is high case, what happens? Okay, what is beta h omega, by the way? Beta h omega is h omega by kt. When T is high, this quantity is going to be much smaller than 1. So when it is smaller than 1, okay, right? So you just to take the second term and try to assess the second term. In case of second term, what I can do, I'll just write that as 1 plus beta h omega minus omega. When beta h omega is much smaller than 1, I can just simply convert exponential of x as 1 plus x, right? So that is what I did. Now minus sign gets cancelled. So average energy is h omega 1 by 2 plus 1 by beta h omega. Okay, now when beta h omega is much smaller than 1, inverse of beta h omega is much larger than 1. What I mean is beta h omega would be much larger than 1 half. So what I'll do, I'll just ignore half. I just simply take that as 1 by beta h omega. H omega cancels. 1 by beta I'll get. What is 1 by beta? Just kt. Okay, so average energy comes out to be kt. When temperature is high, even harmonic oscillator energy contribution comes out to be just kt. Like we are reaching to classical limit or classical case when T is very high. Okay, even with the quantum system. Okay, right? So quantum systems. Now let's say when T is very small. Okay, T is very small. I would say T is small. T is very small. In that case, what happens? Okay, when T is very small, beta h omega, which is h omega by kt, is now larger than 1. Okay, T is very small means it is larger than 1, means beta h omega is larger than 1. Now denominator, whatever I was having in the denominator, I was having exponential beta h omega minus 1, right? So since this is larger than 1 exponential, so I'll just simply have beta h omega. Okay, so let's take that expression again, which is h omega by okay, h omega into half plus, okay, 1 by e beta h omega minus 1. This was the expression. So now what I'll do, h omega half plus exponential beta h omega. Okay, now beta, okay, there is a minus sign comes, okay, right, from the denominator goes to numerator. Now if you see, when t goes to 0, very small, what happens, beta is h omega by kt, which tends to infinity, which implies exponential minus beta h omega is simply 0. So the second term is 0. So average energy is h omega into half plus 0, which is half h omega. So what is this? This is the energy when n plus half. When n equal to 0, I will get this. E of 0 is h omega by 2. It's a 0-point energy. Means at lower temperature, what happens? Okay, the system could exist in a least possible energy. Exist at least possible energy, which is simply h omega by 2. So that is a 0-point energy for any given system, whether it doesn't matter, it's a quantum mechanical or anything, that is a least possible system one can have. Okay, right? So very good. So we'll just take a 5 minutes break and then we'll come up with a Gibbs principle. There also we can derive these things once again. So just to conclude, okay, right? If the things are in equilibrium, let's say more or less everybody contributing same amount of energy. I want to find that what is that energy, equal energy, right? Okay. So for that, there is we will borrow some information from equipartition theorem. What the theorem says is, if there is any contribution coming as a quadratic term in the overall energy, so that contribution is simply equal to half kT, and it is saying don't bother calculating what is that exact energy. On an average, it will be simply equal to half kT. That is what it is saying. Now we have even proved that. Even we proved that using our probability distribution, we calculated the average energy, which comes out to be half kT when temperature is very high, and which is in the harmonic oscillator case, it's going to be simply half h omega when temperature is much smaller. Okay, right? So what we'll do, we'll go a little bit high in advanced level and we'll talk about Gibbs principle. Gibbs principle. Again, it is in the equilibrium situation only. And what is this Gibbs principle? What is this capable of? And we'll see this after the 5 minutes break. So let's take a 5 minutes break. Don't worry, I'll be sharing my entire notes which describes step by step everything. You can follow through and you can understand. Okay. Yeah, I think there is a good question asked by Satish Ji. We'll come and discuss after the break. Okay, so I think we can start again. Right, just give me another minute. Yeah, okay. So I will just give what is a Gibbs principle, and then I will use my hand notes, but it's a lot of mathematics is there. So just to avoid the confusion, okay, right? So basically, Gibbs principle we are actually already encountered. Only we are now giving a name to that, or coining a name to that. What is that? Is okay. Let's say I have a system in thermal equilibrium. Let's say system is in thermal equilibrium. Means it may take some energy from outside and it may leave the same amount of energy to the outside. So absolutely the temperature is going to be constant. So T is constant in thermal equilibrium. In that case, what I can say, the system occupies a microstate. I'm talking about microstate system with energy, microstate with energy ER, occupies with the energy ER, okay, where microstate is, okay, indexed by variable R variable. So what is R? We just saw yesterday three spin systems arranging. R stands for 2, one arrangement. R stands for 3, another arrangement. R stands for 4, another arrangement, like that. Okay. So for all the cases, energy is same. So now what Gibbs principle says, if the system is in such situation, what I will be giving, I'll be giving a probability with this system could exist in a particular state with energy ER. What is the probability? Exponential of beta into ER divided by, if it is a discrete system like quantum mechanical, I'll have summation in place of integration. Okay, so this is the probability distribution given by Gibbs principle. We are already using. Only thing is now we have a name for it. Okay, where as you know beta is just 1 over kT, where k is a Boltzmann constant. So in fact the kT is thermal energy. Okay, now we'll come back to the one of the question by Satish Ji. Now the denominator is summation over eta into b. Okay, beta into exponential er with it. Okay, so this is for a discrete system. Discrete in the sense quantum. Okay, if the energy of the system varying continuously, obviously that would be integrand will be there, exponential minus b, where energy is going to be a function of er or, and I'll say der. Okay, for continuous. Okay, so just to avoid, let me say the ER is a function of some arrangements. Okay, right? Now, this is the situation. Now, Let's looking at the partition function, you can talk about the probability distribution nature. So if you divide like plot probability distribution with respect to energy when t is small, let's say t is equal to zero 0.5, small values. What you see, the expression of probability distribution is decreasing like this. What I mean is the lowest energies are highly probable. You see, lowest energy states, lowest energy states are highly probable. Probability of them is more. The highest energy states are less probable. Now, if you just take, okay, if you just take a higher temperature, let's say T equal to 5, okay, the units of 5, it can be Kelvin or degrees or anything. For a higher case, if you plot, what you get to see is like this probability distribution. So what is here? Highest energy states or large energy states are more probable. So what happens at this point? And right, systems becomes classical. Okay, here systems becomes what? Means lowest energy states are probable. Okay, fine. So this is what the Gibbs principle says. I have a different plots for you. Let me show you that, and then we'll come back to that question. Okay. So let me go through. Just a minute. I have to open lectures. Okay, session 3. You see, for probability distribution for various different temperatures. Okay, so I have temperature 0.5 units, some units. I'm not saying which Kelvin or degrees. 0.1, 2, and 5. The trend, if you see, increase in the temperature, increase in temperature, what is happening? The highest energy states are becoming more probable, lowest energy states are less probable, which means if you just take atom, okay, right? Okay, so as temperature increases, electron in the ground state goes to the higher state and it may go out of the atom as temperature increases. So that is obvious. So the electron existence in higher states becomes more probable. Okay, right? Fine. Now let's apply the Gibbs principle to classical harmonic oscillator. We already did. Okay, just for the sake of, in terms of Gibbs principle, if I have to derive what is the average energy of a classical harmonic oscillator, how do I find? First I will find out what is its energy. Okay, energy is simply p square by 2m of m omega square. What is a classical harmonic oscillator? It is simply a spring mass system. Okay, mass is there and spring constant is equal to m omega square and mass m. Okay, and it is probably making an oscillation about, okay, it is making a oscillation about some x displacement. Okay, right? So in this case, first of all, if there are such classical harmonic oscillators, several are there. There are several spring mass systems. If I take them together, okay, now in this case, you see, the energy can be continuously varying, no need to be discrete, because one spring mass system would contribute some energy, another spring mass system contributes slightly incremented in that. So it's a continuously increasing. In that case, the Gibbs principle becomes an integrand instead of summation. Okay, now so there is a contributions coming from p, there is a contribution coming from x. So my probability is p of x comma p. It's a function of x comma p. So instead of writing pr, I will just write p of x comma p. Okay, Now, so adopt the expression of probability distribution accordingly. Okay, adoption. When you do it, okay, I can get in the denominator a double derivative is there, because corresponding to dx one derivative, corresponding to dp another derivative, there is a h term I am going to divide. So what I mean by h term is, okay, it is just to take care of the dimensionality. What is the dimensionality? Here, the actual expression, I have a derivative with respect to energy. In the case of the, when I convert to the position and momentum derivatives, okay, see the dimension of dx and dp. It is an angular momentum. But what is the energy? Energy is, okay, energy is angular momentum into some value. Okay, so if you just divide by Planck's constant, you will have the exact dimensionality match. We'll see why do I need to divide by Planck's constant later. But the time being, what you can do, in the box I have given how the dimensionality will be matched when I just divide it by Planck's constant. Okay, so that 1 by h, you just bring it to the outside of the integrand, and you see carefully, okay, in the denominator, that is the partition function. I'll just try to find out what is the partition function. Okay, so explicitly substitute what is E. We know E, just substitute here. Okay, when you substitute explicitly A, there is a first quadratic term with the dp integrand. There is a second quadratic term with the x square with a dx integrand. So literally these are two Gaussian functions or two Gaussian integrals. We already seen what is a Gaussian integral contribution. It's just a square root of pi divided by whatever is multiplying into the quadratic term. Accordingly it will come. For the sake of your knowledge, I have even showed you how to find the Gaussian integral. Let's say I have a Gaussian integrand something like this. Integration with minus infinity to infinity plus alpha square into z square into dz. Okay, this is a Gaussian integral for you. Gaussian integral. Okay, now what I'll do, let me say alpha z is x. In that case, alpha into take the derivative on both sides. Alpha dz is dx, dz is dx by alpha. Okay, so you substitute those conversions. Wait a minute. Okay, just a minute. Yeah, where did I lose? Wait a minute. Yeah, so if you substitute those conversion into the Gaussian integral, what I'll get? 1 by alpha summation over minus infinity to infinity exponential minus x square into dz. Very good. So what it is just an exponential of minus x square into dx with the integration going from minus infinity to plus infinity. I want to find this, but it is very, very tricky. So what I will do, let me say, instead of finding I want to find the integration square, square root of that, sorry, square of that. Okay, so I can't just, when I multiply integrand with itself, I can't keep the same x. I want to use a dummy variables to avoid multiplication of the terms perfectly. So what I'll do, the summation over minus infinity to infinity minus x square as a one of the integrand minus y square as an exponential another integrand. Okay, so now it's a double integral. On the left hand side I square. This is how a trick people play in mathematics. So what I'll have, minus infinity running from, for the both the integrals, one is with the dx, another one is dy. Okay, now again if you see, it's a Cartesian coordinate system kind of a thing. It is again double integral is very, very tricky to find. If you go to polar coordinate, it becomes very, very simple. What I'll do, I'll introduce x is equal to r cos theta, y is equal to r sin theta, where dx would be dr cos theta d theta and so on. Okay, if you do that, okay, let me remove this. If you do that, x square plus y square is going to become x square and y square is going to become simply r square. Okay, see, simply becomes r square. Dx into dy becomes r d theta dy. What I mean is, so dx into dy is a small volume element in a surface element in polar coordinate Cartesian coordinate system. If this is I, this is j. So this quantity is dx, this quantity is dy. So we are actually finding small area element. In the case of polar coordinate, small area element would be, okay, small area element would be r, okay, dr. So this would be dr, r into d theta. This is theta. Okay, let me give you that explicitly. R d theta is r d theta is this quantity and dr would be this quantity. So small volume element there is r d theta, dr is a equivalent to dx dy. Okay, so in place of dx dy I'll put r dr d theta and you just substitute. What it will become? It will become double integration, one integration r running from 0 to infinity. Theta is running from 0 to 2 pi. See, theta runs from 0 to 2 pi, r runs from 0 to infinity. Okay, so d theta, there is no other integrants with the theta, so you can simply integrate out. It will become 2 pi, and only left with is integration running from 0 to infinity, exponential minus r square r into dr. Okay, now what I'll do, I'll introduce another conversion. R square is equal to t, where 2 into dr, r into dr would be dt. Okay, once I do that, it becomes I square is integration over 0 to minus 0 to infinity exponential minus t into dt divided by some 2, which comes from the conversion. Okay, so that 2 and this 2 gets cancels. I left with only pi. So integration is 0 to infinity minus exponential t into dt. So if you integrate it out, what you will get? Exponential minus t divided by minus 1, 0 to infinity. If you substitute the limits, what you get is basically pi value. So I square is pi. I is simply square root of pi, right? Now, okay, so in place of x square, I have alpha square plus z square. So which means I need to have this 1 by alpha as a term, which was earlier we had, so that you integrate, put it up. So what I will have? Square root of pi by alpha is our term or integration of I here. Okay, so this is equal to square root of pi by alpha square. If you want, put it inside. Okay, now we know that. Now I can find what is the contributions coming from kinetic energy, what is contribution coming from potential energy, just by use this and replace the constants accordingly. And what you will get, the overall z is simply equal to k beta k into t divided by h omega. So Boltzmann constant, sometime I will write k, sometimes I will write k into b, both are same. The beta stands for Boltzmann constant in the subscript. Okay, so z is simply k into t divided by h omega, or also sometimes I'll write 2 pi b into h omega. Okay, what I mean, h by 2 pi is 1 by h omega, h cross omega, B, if you put it in the numerator, it becomes KB into T. Okay, so this is also right and this is also right. Okay, so mean energy, as you know, mean energy of any system is the derivative with respect to beta and partition function ln z. Okay, right? So you can have that explicitly find what is this term. Okay, so I have it here for you. There are few terms. There is a constant 2 pi, there is a Planck's constant, there is a beta, there is a omega. Okay, so there are all constants. You can put it up and you just derivate with respect to beta. Only this is the term which is going to contribute. Everything else is 0. So what is that contribution? Minus of kT. So I want to have minus of minus. So I'll have kT is the average energy. Okay. Now for a quantum harmonic oscillator, for a classical harmonic oscillator, I got a average energy is kT. That is what we did earlier also. Now for a quantum harmonic oscillator, even if you find through the Gibbs principle, you will find the same way what we did earlier. Okay, we did this earlier. So we took the energy, substitute inside the partition function. Okay, right? So once you do, there is a way. Final expression is average energy is something like this. Now I have to assess when time is equal to temperature is equal to low. In that case, what happens? I will have a classical harmonic oscillator 0 point energy. When temperature is high, I will get the overall energy, mean energy is just simply Bk into T. Okay, that is thermal energy. Right? As somebody was asked a question, Satish ji, I will come back to your question once I am done with these descriptions. Okay. Now let's plot mean energy versus the temperature. Okay. As you can see, there is a dotted line is a classical harmonic oscillator. Red line is quantum harmonic oscillator. As temperature increases, you see both are same. When temperature is low, both are different. You see, there is a difference. The quantum harmonic oscillator starts from, you see, that is very important, starts from 0 point energy. There is no lower than 0 point energy in a quantum systems. By default, it exists with that level. Okay. But in the case of classical harmonic oscillator, a spring mass system can exist with a zero energy. You know why? The spring mass system, if I am not giving any energy of oscillation, any deviation, it remains without any oscillation. So the zero energy is possible. So E minimum is zero possible. But harmonic oscillator, electron revolving around, we can't have zero energy as a zero. So this is a 0 point energy. Okay, so that is what is shown here. Okay, fine. Even if I go from higher temperature, take a quantum harmonic oscillator, go for higher temperature means what? I'm clubbing all the atoms into one, making a macroscopic system. Macroscopic system, the temperature is going to be much larger. Okay, that is what I was discussing here. There is a partition function which helps me to understand this. What is that is, let's say I have a macroscopic system. You see, there is a large macroscopic system. Inside that, there is a microscopic systems. 1, 2, 3, so on. Macroscopic system means a collection of a clump of solid. Inside that, there are atoms. So each atom is a microscopic. Okay. Now, there is a statement here. Knowledge of these microscopic systems could give information overall of the large system. You cannot go other way around. Knowing the information of large system, you can't find what is the information of small systems because you actually lost the information. So yesterday somebody was asking local and non-local. Okay, local is quantum. Non-local is classical. The moment you come from larger level, you can't have the information at a very tiny level. We can't, it will be lost. Okay. Now, using a partition function, it is possible through the partition function, which is Z. Okay. So partition theorem says, equipartition, like any partition theorem, it says using the Z, I can find the mean energy. Okay, I can find mean energy, mean gas pressure, mean entropy of the system, mean energy dispersion of the system. How? We just use that method, probability distribution method, to find that. How? We'll list down all the accessible states. From each state, what is the energy? We sum all the average energy divided by total accessible states. Okay, and we'll get the average energy. Okay, and we'll find the average gas pressure. How we can find the gas pressure from each contribution from each location and sum them up divided by overall parts. Okay, so that is what we can do. Now connecting microscopic to microscopic transition, if I want to do, how and why we want to do is, let's say I have an ensemble of qubits. Let's say IBM 5 qubit system. Qubit 1, qubit 2, qubit 3, qubit 4, they are well connected. Okay. Now, am I allowed to write a partition function for this? Of course, you can write. You can see the arrangement. In each arrangement, what is the energy coming from? And you can just sum all the possible scenarios. Okay. Z is just summing all the possible scenarios. It is not the energy, remember, it is just a partition function. I use the Z to find the mean energy. Okay, I can do that. Okay. Now, there is a description here, level of difficulty in the system calculation. Okay, for ideal gas, if you just take, means the material gas, if you just take, particles are there, they are not at all interacting, they are freely like they are almost ideal, they are separated. In that case, it is very easy to find the quantum states, individual quantum states and individual partition function, overall partition function. But when all the atoms are interacting like liquids, okay, I'm not saying it is impossible, but it's slightly difficult in comparison to non-interacting case to find the information about the system. Okay, to get the mean energy and any mean value of parameters, we can do it, but we have to take into consideration of the interactions of the system. Likewise, we need to take, for example, in 5 qubit system. Okay, right? Okay, so here the classical approximation. Okay, now classical approximation, since I'll take a system approximated to be classical, then its energy would be just energy of contributions coming from, or if n particles are there, qn to q1 to qn, pn to pn. Obvious, right? Okay, and its corresponding probability distribution, sorry, partition function is just whatever we had so far. Now if you see, earlier we used a phase space representation where momentum would increase in such a direction, position increase in such a direction. There is a small change in momentum and small change in position. If you multiply, you get a small unit in that phase space. Okay, right? So system moving from one location to other location is nothing but evolving from one location to other location. Okay. Now the each unit is having some unit. What is that? H naught is equal to delta Q into delta P. Okay. But how many such units would be there in dq and dp? Okay. How do you find? Take the entire volume of dq's and dp's, divide by volume of each one. What is the volume of each one? H naught. Okay. I will take the nth power because there are n systems. Okay. And if you divide that, you will get simply the number of cells in the system. Okay. So that is just immaterial right now. Just ignore it. Okay. So what is most important is, let's say I have a quantum mechanical level expression. How do I transform with a classical approximation? Okay. So what you do? A discrete, sorry, quantum mechanical to classical. We need to convert this integration, sorry, the summation to integration. Okay. Where the integrand element should be properly addressed. Okay. The energy has to be expressed properly with a corresponding expression in terms of position and momentums. Okay. Right. Yeah. And few advantages of this physical quantity calculation using partition function is, what are the advantages? Let's consider a state represented by R having some ER is slightly changed by a quantity E naught. What I mean is, let's say a system is having some ER energy, some energy is coming from outside. Okay, how much energy is coming from outside? Let's say E naught energy is coming from outside. Okay, so there the new energy of the system is ER just star. So new energy is there. So classically, the partition function also changes. Okay, means the number of accessible states also changes with the change in energy, right? So let's say I want to find what is that partition function. I'll call it as Z star. Old case, the partition function is just Z. New case is Z star. Now, if you substitute the new energy value and rearrange the system, and you see the new partition function is equal to old partition function multiplied by simply exponential of minus beta epsilon naught, where epsilon naught is the energy coming from the surrounding. So log of new partition function is log of z old partition function minus just beta epsilon naught. Okay, and as we know, average energy is derivative with respect to beta log of partition function. So let's try to find that here. And what you get? The new average energy is simply old average energy plus whatever added new energy, whatever energy coming from outside world. So that much simple things would become in finding average energy when something is supplied from outside. Using partition function, you can find the new average energy value by just adding that energy value to the old energy value. Okay, it is just like we have, let's say we have evaluated the exam. Okay, the average of a entire class is some value, and later on some students comes and tells us that you have made a mistake in a particular question, so the question is wrong, so the marks for that particular question should be raised, or you have to give by default marks for everybody. Okay, with respect to that question, even whether they have answered right or wrong, so you have to give the marks because so that particular question was wrongly asked. In that way, what happens? The old average would raise as you add the marks to everybody. Okay, so same story here. Old average is raised by a quantity E naught when I supply the energy to the system in general. So if I have a collection of many microscopic systems, each one would be arranged in such a way that is overall energy is ER. When I supply the energy to each one of them, so the average energy is raised by some quantity E naught. So that information we can tell in general, but the proof is there through the partition function. Okay, right? So similarly, you can also find the entropy. Okay, entropy is connected to even partition function, and also it is connected to the average energy. From there, you can find the entropy. Okay, so interestingly, what you see is entropy is remaining the same. Okay, so which is thing which needs to be discussed. It is actually called um, Gibbs paradox. So I have in my later slides. So we'll come to that. So now let's talk about the systems which are weakly interacting. Okay, right? So let's say I have a system here and it is divided into two parts like a prime and a double prime, right? So each one is having energy ER and ES. Okay, so ER corresponding to A prime, ES corresponding to A double prime. Now, what is the real scenario? Real scenario could be helium and neon in an ideal gas mixture. Okay, wait a minute, I did something. Yeah, so helium and neon atoms in ideal gas mixture will possess different degrees of freedom. Okay, one system may have a translation motion of its constant mass of molecules. Okay, another system may have rotational motion of the molecules with respect to their center of mass. So there are two different systems, different energies. Okay, they may be weakly interacting. That is the situation I was talking here. The A is divided into A prime and A double prime, and their energies also I will call ERS, ER prime, ES double prime. Okay, so when I have a subscript ER and ES, why do I need a double prime and single prime? Just to connect for the overall system, I have that primes. Okay, now what is the partition function for that system? Okay, I know the energy, let's substitute and find the partition function. So partition function, if you explicitly see, it is just a product of individual partition function. Beautiful, right? So if you just to take a log of that, the summation of individual partition logs is overall logs. Okay, so average energy is also simply sum of individual average energy. Okay, see, this one is contributes for average energy for the first system, second one contributes for the second system. Okay, so partition function is just a product of physical quantities and it is simply involves sums. Okay, example energies. Okay, now we can bring in, there are so many systems, many body systems. Okay, no more just two systems, I have many systems where, okay, so there is a kinetic energy, there is a potential energy comes from positions. Okay, so potential energy I can't explicitly write down. Let me write down some expression U. Okay, which would take into consideration the interaction between the molecules and their molecules individual potential energy. Okay, kinetic energy is straightforward, very easy. You can individually write half mv square for each element. Okay, when the system is not at all interacting, negligible, you can simply say u is equal to 0. That is a simple ideal gas scenario. So in that case, partition function is this quantity. Okay, right? So you can find the partition function, okay, from the partition function. So I'm not going to the derivation, it's very lengthy. So what you get is simply overall energy is individual energy multiplied by number of overall particles, specifically saying each contributions comes out to be k into t. Okay, that is a mean energy, by the way, for the molecule. So okay, right, so the other calculations you can do entropy in terms of z. Okay, right, so that is what the Gibbs paradox. What is the Gibbs paradox? Okay, so let's understand what is a Gibbs paradox. Let's say I have a system A. I have a system A prime and A double prime. A is having A prime and double prime. Let's say individually they are separated. Okay, right? They're identical and there is a partition between them. It has N1 particle, V1 volume, and they are both are having same temperature. right? So I would think usually if everything is same, when I remove the partition, what I will feel? I'll feel everything is same. There may not be any change in the system, no orderness in the change. Okay, but what happens? Let's choose that as per my entropy equation from the partition function. So this is the expression what we have. Okay, now if the partition is removed, then what happens? We'll think that the entropy of the left side, entropy of the left side, both are same because same number of atoms, same amount of volume, same amount of temperature. Okay. So what is the overall? Overall is just simply twice of this, but remember the volume got increased to double and temperature remains the same. So other terms remains the same. Where there is a alpha is, sorry, sigma is there. Sigma is some quantity which is derived earlier. Okay, sigma is derived. You can follow that. So I'm not going to derive that. It's a very, very lengthy expression, lengthy derivation by the way. Okay. So now, okay. So once I remove the partition, this is the entropy. Okay, I assume that when I remove the partition, there is not a mix happens, and the overall entropy of the system is just twice of individual entropy. So I'll just do as per the overall entropy, and what is as per my assumption. Okay, if I try to find S minus S2 into any one of the entropy, I am going to get some difference. It should not be right. Okay, when I think that when I remove a partition, the two systems are alike. Okay, two systems are alike, so they should not mix. That is what I assume, but they're actually mixing. Because of that, I get one overall entropy is one expression. Okay, my assumption is just twice of something. If I take the difference, I'm getting that. Okay, so to address this, what you should do? Problem here is when I remove the partition, the volume available for S prime and S double prime is actually doubled. It's not single. When you do this, it will be addressed. Okay, right? So the Gibbs paradox is removed when I address the system properly. Okay, so disorderness may increase or decrease depending on the availability of the location, the area. So even when if they are not mixing up, when you remove the partition, probably later times they may go and situate different places. They may rearrange their orderliness. Their entropy may be rearranged. So that is the Gibbs paradox for you. Okay, right? So how much time we have? 15 more minutes. Okay, so another way of correction, Gibbs correction, is also discussed here. You can go through it. Now we have plenty of time to come back and discuss few questions. Let me see one question here. Okay, right? Yeah. Okay, so let me come from all the way top and see if there is any questions. Okay, no questions till 3 o'clock. 3, 4. Okay. Okay. Yeah, I think 343, Satish ji question. Okay, so let me read the question for you. For 1 microkelvin, the KT value would be, okay, 8.6 into 10 to the power of minus 12 electron volt. Okay, let me write down that. I think that's the best way to do it. Okay, what is being said is, okay, let me take a red, blue, black color. Okay, right? So for 1 microkelvin, okay, the KT value is 8.6 into 10 to the power of minus 12 electron volt. Okay, fine. So what is the minimum energy required for a quantum materials? I hope the minimum energy depend on the material. Now remember, okay, so this is a 1 microkelvin. Microkelvin or a millikelvin. Okay, so you remember we use, right, 50 millikelvin for, okay, for keeping the quantum qubits intact in superposition. Okay, so that is what being done by IBM in their quantum computers. Few millikelvins are at least 50 millikelvin. Okay, now you are talking much smaller than that. Okay, 1 microkelvin, and this energy is much smaller. Now that means this energy is not sufficient. Let's say if we just take a nucleus, ground state, excited state, the next excited state, we take a snapshot of it and plot it here. There is a ground state, there is an excited state, there is a next excited state. Okay, so let's say electron is here. Okay, if I supply a photon of energy, separated whatever energy separation delta E, so the electron would go and sit here. Now I have to worry if a surrounding energy or temperature supplies energy equivalent to this value. Okay, right? K into T. If that K into T is more than this separation, what happens? When I want to have a superposition between 0 and 1, I'm sorry, let me take that 0 and 1 instead of 2, 3, 0, wait a minute, 0, 1, 2, and so on. Okay. So when I have a superposition between 0 and 1, so if the KT is much larger than the energy separation, let's say delta E prime. Okay, delta E prime. In that case, what happens? The electron no more exists in superposition, it jumps out of it. So I would lose the quantumness, I would lose the qubits here. Okay, right? So what is the minimum energy required for a quantum materials? Okay, okay. So what is the minimum energy? So you just calculate anything above 50 millikelvin. Okay, anything about 50 millikelvin is going to be, temperature wise, is dangerous for the system. How dangerous? It is going to push the electron out of this 0 1 superposition, push to somewhere else. So the minimum energy I need, I would be very greedy, I would need a energy is 1 by 2 h omega, 0 point energy I want to have, so that I can have absolute control on the system. So that is not possible, by the way. So I will go to very close to that by reducing the temperature of the qubit. Okay. So once you see in the plot I have for you. Okay. Wait a minute. Where is that plot? Okay. This plot, na? Temperature versus. You see? Let me remove this everything so that you will understand. Okay. So what I want, okay, I want to have the least possible energy, which is simply h omega by 2. I can't have more than that. How much temperature I can reduce? I can reduce up to some level here. Okay, right? This is somewhere close to few millikelvins. Right? You can't go less than that. So where the quantum and classical is very good, nicely separated. As temperature goes and goes high, what happens? The closeness between quantum and classical is very narrow. So I might lose what is quantumness, what is classicalness, I might lose that. Okay. So coming back to your question, what is the minimum energy required for quantum materials to behave to be a quantum. So minimum energy required is our own temperature should not disturb that. Anything less than that, I'm fine, I can do the computing. Okay, so that is the answer for your question. So there is one more question I see. Okay, so yeah, can we use Ising model for quantum qubits? Yeah, of course, right. Yeah, Ising model is an extension of whatever we discussed. Okay, I think it will come in the quantum material study in your QTs. Okay, maybe QT 08 or so. Yeah, it will be discussed there. Remember there the Hamiltonian would be, I think yesterday also I was mentioning, the Hamiltonian would be incorporating the way the systems were treated with the Ising model. Okay, right? Okay, so for financial fraud detection, we can use this in quantum machine learning. Yes, people are using as of now, using the Ising model optimization technique they are doing. Okay, yeah, it is one of the technique. Okay, then there is one more question here. As a statistical physics be about solid liquid gases, the quantum computing is in which state? Very good question. We'll answer one by one. As a system has to use liquid nitrogen or oxygen, please clarify. Then does it has all the three states? Okay, a very good question which actually needed to be clarified. Thank you, Rauji. Keshavarao. Okay. Remember, in the cryogenic cylinder, there are setups like a chandeliers. You see, inside a chandelier, at the bottom, we have a quantum chip. Okay. Now, this is a cylinder, you know. Yesterday I showed you a figure. I'll show you today also. Now, if you want, I can show you now also quickly. Save. Okay. Okay, I might. Okay, do I have it somewhere? Okay, wait a minute. I'll just come. Okay. Okay. Anyway, now looks like it is somewhere in my Google Slides, I think. Okay. So I'll show it. I think yesterday I showed you, I guess. Okay. Now come back to here. Now this is a quantum chip. What people do is layer by layer, they will fill it liquid helium, liquid hydrogen. Okay. Okay. Liquid form. So why different liquids? Because the liquidation happens for them with particular temperature. So this is let's say few Kelvin. Okay, right? Let's say few like 100 Kelvin. As I go lower, I'll have few millikelvin. Okay. So everything is liquid. Only thing what it is ensuring, the temperature of this chip is going to be at 50 millikelvin. That is what it is going to be created. Now remember, so this has nothing to do with the phase change or anything. So phase change for statistical physics, changing from gas to a vapor or gas to solid and liquid and so on. That has nothing to do with here. The liquid is being used to just retain the temperature of the chip to millikelvin. Okay, there is nothing phase transition of the used cryogenics here. Okay, so what is the statistical physics role here? The statistical physics role is if you just take the transmon chip, okay, there is a qubit 1, there is a qubit 2, there is a qubit 3, qubit 4, qubit 5. They're all interconnected. Okay, they're all interconnected. How well they're interconnected? What is their interaction? when I see them as a whole system, how they will behave here. Okay, so there are individual guys, they're together, how they behave here. So the interaction and their overall evolution is studied or analyzed by the statistical physics. Okay, you can also say quantum statistical physics. That's all. So the phase change and all, nothing, no relation here. Okay, right? I agree that as a solid state, statistical physics is all about studying the solids, liquids, and gases. You know why? As you see, gas, if you just take, particles are hardly interacting. So we can treat them individually. The moment it becomes liquid, they are very close to each other. Okay, they are flowing. So in that case, we can treat them with weakly interacting particles. In the case of solid, you say they are very close, packed arrangement. So there, the interaction is very, very important to be addressed. So there, so the study of gases, liquids, and solids, it's all becoming different zones, and all those different zones are studied using solid state physics. Okay, in the case of quantum computing or quantum hardware, whichever we are talking about, so the only chips are involved. Chips actually represents a collection of few qubits. For example, if you can take a D-wave quantum hardware computer from Canada, they have few thousands of qubits realized out of something called quantum annealing. Okay, there 1000 qubits are interacting. So they are probably we use a solid state physics of weakly interacting qubits or weakly interacting microsystems. Okay, right? So that is the answer for your question. And there is a one more question as here. As a system has to use a liquid nitrogen, please clarify, does it has all the three states? No, this quantum system doesn't have all the three states of gas or solid or a liquid. It has, at the most, you can treat them as weakly interacting qubits, very close to gases, or slightly slightly leaning towards the liquid because they're weakly interacting. Gases means absolutely no interaction as such. Okay, so my quantum qubit collection is lying between gas to the solid liquids. Okay, that's all. There is nothing more than that. So liquid cryogenics being used just to cool the system, nothing to do about the phase transition there. Okay, so thank you Kesharavji for a nice question which needs to be addressed. Okay, so there is okay, Satish ji, there is a temperature window for qubits, a few microkelvin. Yeah, yeah. So few microkelvin is 50 kelvins to close to 100 Kelvin. If I will have a better qubits without losing their quantumness and superposition. Okay, next question by Veeramanikkam ji. Any relation between energy state and these principles of quantum computing system? Yeah, that is what we are trying to do. Energy states, na? We are trying to write for a nucleus and an electron and the next level and the next level and the next level. See, we have n equal to 0, n equal to 1, n equal to 2, n equal to 3. What is the relation of energies? It is just h omega n plus half. This is the quantum mechanical energy of a quantum harmonic oscillator, or like an electron. Okay, so you are saying what is the relation between energy state, and these principles of quantum computing system? So the relation is this. I will choose a combination of any two states and write them as 0 ket and 1 ket. They ensure that electron would exist in between any two orbits. Okay, it does the oscillation. If I am doing with the natural atom, this is what I will have. If since the natural atoms are so much fragile because around surrounding temperature I can't have a absolute zero, what people do, they will create the LCR circuit. What is this LCR circuit is? Okay, L is inductance, capacitance, and internal resistance. If you just take this, connect to a battery, okay, LCR. Basically, this is an oscillator for you. Oscillator. What is oscillating here? The charge on the capacitor is oscillating. How it is oscillating? If your time versus capacitor charge on the capacitor, if you do, it sometimes it's a some 10 coulomb and drops to 0 coulomb and then goes to 10 coulomb and it's just oscillating. So I'm just giving an ideal situation. Basically, it is just decreasing and increasing and decreasing and increasing. It's like, okay, that is what we see here. Now, the LCR circuit is like this. Basically, it is oscillating between two kinds of quantum mechanical states, 0 coulomb and 10 coulomb, the capacitor. Ideal situation. It's not like that. Now, if I have the LCR circuit, okay, and connect that to some oscillating power supply. Internal resistance is there, by the way, somewhere inside. I'll not draw explicitly. If I do this, you know what happens? A capacitor can exist with the various possible charge states. Let's say 5 coulomb, 10 coulomb, 15 coulomb, and say 20 coulomb. Now you see, there are all quantum in nature, the sum of some collection of charges, right? Okay. So the separation is, you see, 5 coulomb separation, 5 coulomb separation, 5 coulomb separation. Okay. But okay, that means I can just pick any two states and you can create a superposition out of it. Okay. That is what people thought. Okay. So if I create a superposition between 5 coulomb to 10 coulomb, what happens? The information may even lose to 10 coulomb to 15 coulomb because they're also equally separated. Okay. So for that, what people did, instead of inductor, they replaced with the Josephson junction. What is that Josephson junction is? There is a superconductor, there is a superconductor, there is an insulator. Okay, if you have Josephson junction, JJ junction, Josephson junction. If I have, and then you cool this Josephson junction to millikelvin, what happens? In the superconductor, electrons gets pair up and they create something called Cooper pairs. These Cooper pairs would not keep quiet. They even punch through the insulator into other part and then just do back and then do the oscillations between back and forth. Basically, they are inducing effect of one superconductor motion, their motion into the other superconductor part. They're doing oscillation. So it's a kind of an inductor effect. Okay. Because of this inductor effect, if you replace inductor with Josephson junction, they'll write with X mark, okay, and have a main oscillatory field. What happens now? If you find the capacitor charges, this time what you see is the first one is separated by 5 coulomb. That's a 5 coulomb to 10 coulomb. Next one is separated to, okay, 13 coulomb. So the separation energy is 3 coulomb. The next one is 2 coulomb. The next one is 1 coulomb. Okay, so this is 15 and 16. So unequally spaced quantum states are available when I make a Josephson junction into the LCR circuit. So this is actually transmon. Okay, so this entire setup is actually represented by 1 qubit 1. So that is what the IBM chips are having. Okay, in the IBM chips, there are locations. There is a Q1, Q2, Q3, Q4. They're all internally connected with the radio frequency waves. Okay, right? So the LCR circuit, you may not see exactly like this. You would see there is a Josephson junction created by very superconductor. Around that, another superconductor created like this. Okay, so the insulator is in between. Okay, they're like this, and then when it comes to capacitor, they will have a capacitor plates like this. Okay, why they are like this? Just to increase the area of the each plate, they will have something like this. Okay, right? So LCR is like that. The incident radio frequencies onto this setup. So that will induce some change and induce a superposition state into this. Okay. Coming back to your question, any relation between energy state and these principles of quantum computing? I think I answered that. How do we choose the number of qubits for quantum neural networks? Okay. Uh, Energy states, yeah, the energy states are, yes, energy states are this relation. And in the case of transmons, the energy states are like energy states are would be some, what is the state with the capacitor would exist with which states. Those are the things which is closest explanation. Okay. Now let me go to the another question. How do we choose the number of qubits for quantum neural networks? Okay, so it's all depends, right? If you have a large data, you want to process all the data, depending on if the size of the data is n, capital N, you need to take a small n number of qubits to store all the information and process. But what people do, they will take few qubits and start doing part by part using neural networks. Okay, so depending on your GPU, how many number of qubits it can process, okay, at a given time, how many qubits it can mimic or simulate, and you would be dealing with that much amount of data at a given time. If less number of qubits are there, means more amount of time is required for processing this data. So it's all depending on your GPU. But when it comes to the greedy scenario, right, if you are able to generate n qubits sufficient for your all data, well and good. So uh, if number of qubits you can mimic is small, means you have to do a lot of computing. Okay. Liquid gas, for if liquid gas fine, then how to how relatable with the waves and particles form of qubits, including liquid form? What is the relation among all? Okay, right. So please clarify one thing for first now. Okay, there is something called a de Broglie wavelength, h by mv. Okay, the wave nature of any given system would be measurable only when mass is very close to the quantumness. Means, let's say 10 to the power of minus 34. You know why? The Planck's constant comes with the 10 to the power of minus 31 or 35 or something like that. Okay. So there's a Planck constant in the numerator is 10 to the power of minus 31. The same range denominator I need to have. Okay. The velocity could be close to the velocity of the light. In that case, what happens? The wavelength comes out to be a measurable wavelength, angstroms. Okay. Only in that case, I will have a wavelength of 1 angstrom. Okay, 1 angstrom wavelength. So that is measurable. Any other value less than this is immeasurable. When it will happen? If I go for a larger and larger system, if the denominator is larger and larger, then overall lambda is going to be much smaller than that. Okay, so coming back to your question, how relatable with the waves and particles per qubits, including liquid form? What is the relation among all? Okay, so the qubits which we are choosing right now here, where is my qubit architecture? Okay, so qubits which we are choosing here, they are almost like a gaseous phenomena, means they are not at all interacting. The interaction is created by some radio frequencies going from one to the other through some waveguides. Okay, so the interaction is like that. Okay, so yeah, in future if you come up with a quantum qubits interacting solid state based one, there probably we might need to bring in the more statistical physics to understand that. Okay, right. So The relation which you need to choose to understand is this relation. When to have quantumness, when to have classicalness. By the way, our LCR circuit which we are choosing, they're actually having a nice wave particle duality. They are already in a quantumness. So we are treating them individually. Okay, right. So the final question by Ravi ji, if one Cooper pair or a qubit in superconductor is formed below TC, the threshold temperature, then it leads to create more Cooper pairs. How the scalability of qubits can be controlled in such case? Okay, very good question again. Okay, so if you see Josephson junction, superconductor, insulator. Okay, so Cooper pairs forming, it is not like two atoms are clubbing each other and they are like they just traveling like a pair, or this is they're traveling by holding hands. It's not like that. So the moment you cool the superconductor to the few Kelvin, millikelvin, what happens? The situation is created in such a way that electrons flowing together. That's all. Earlier they're separated apajadously. The moment you reduce the temperature, they come very slow, very close, and it appears to be like two of them traveling together. We think that they are friends, right? But in fact, they are not, may not be friends. So the Cooper pairs are formed two with each other. So depending on temperature, how many form? That like how many form, how many are oscillating from left to right, that is all depends on the situation. Okay, so this has nothing to do with how many qubits I'm realizing. Okay, so in LCR circuit with the Josephson junction, okay, doesn't matter how many Cooper pairs are formed within a Josephson junction. What matters is the entire setup is going to give me two possible quantum states or not. In that I am able to create a superposition or not. That is the important. Okay, right? So one more thing, the temperature if you go on low and lower doesn't mean another electron comes and meets with this Cooper pair and increases the size of the Cooper pair. It's not like that. So at a given point, doesn't matter how much temperature you reduce, two electrons happen to travel together. That appears to be like a Cooper pair for me. So that is what the Cooper pair is. It's not like two are like connected by some means. No. Okay. So the solid state physics discusses that in detail in the quantum materials. Probably there, I think this is elaborately needed to be discussed. Okay. Right. Okay. So we are past 15 minutes by above 5 o'clock. So I will stop at this point and I'll hand it over to the organizers. Okay. Right. So I think yesterday I've shared the entire notes. Okay. So let me save this for today. I've shared this also, today's notes. So today is 27th September. September. Okay. Save. So I will save these notes and also upload today's notes. I think on Monday. No, not on Monday.
The next will be on 3rd October.
Okay. So next on 3rd October, I would be right. So there is a continuation for this is coming. Okay, so if we can see the schedule, continuation comes is on 15th and 16th. Okay, and during 15th we talk about something called Fermi-Dirac statistics, and 16th we'll talk about Bose-Einstein statistics. Maybe it will conclude a little bit more and inform more about quantum systems when we have these two discussions in the later part. But on 3rd, I will be discussing a little bit more on the entropy of the system information. Okay. So what is this information science in the digital communication, and how ordered it is, how to represent that, how to measure that. So that is going to be discussed using Shannon entropy. Okay, right? So as of now, solid state physics is on hold. It will come back on 16th and 15th and 16th. Okay, right? Okay then. So Majumdar sir, please take over.
Thank you, sir. Thank you for this nice session. I can see the so many questions and so many good questions. Actually, that means that the participants are actually greatly involved in this presentation. So yeah. Today would be the ninth session, which is over today, and next the Dussehra holiday is coming, and due to which we'll take a break up to October 12th, and on October 3rd we'll come back on this. So once again, happy Dussehra to everyone in advance. So all of you, please enjoy the holidays, and let's come back on 3rd October. And happy Dussehra to you, sir.
Thank you, sir. Majumdar sir.
Uh,
Same to you, sir.
Thank you, sir. And happy Dussehra to you, sir. Anil, sir, if you are there.
Thank you, sir. Thank you, Mazumdar sir, and thank you, Ashad sir. Thank you, Sudhakar
Thank
sir, and all the participants. So we
Anil
have
sir.
till 2nd of October we have holidays, and 3rd we will reopen again.
Right, sir.
Sir, what is the deadline for this quiz?
The quiz deadline is Sunday evening. We have extended for one day, and now it is the Monday night. It will close. So they are getting 2 days, another 2 days.
Great, great.
Right, sir. And one more announcement I would like to make to the participant. Many of you have not accepted the Canvas invitation. Please do kindly remember that all the quizzes are mandatory for the certificate that you want. And before, if you do not attempt, because this Monday after that will not extend the date for this quiz one. So kindly accept the Canvas invitation and complete quiz one by Monday positively. Otherwise, you will lose out on this one. So again, kindly remember that, and we'll send the we'll resend the Canvas invitation all once again today by tonight. If you have not received the mail, kindly let us know. We'll be sending it in some time, and please join it and do the quiz. Otherwise, yeah. So again, once again, happy Dussehra to all of you. Please enjoy that, and also please do the quiz. And thank you once again. Let's meet on 3rd October once again at 3 p.m.
Yes,
Thank you,
happy Dussehra
thank you,
to all the participants.
thank you,
And
sir.
Anil
Aswa
sir.
sir, thank you.
Thank you,
Uh,
everyone. Thank you,
I
sir.
have uploaded the lecture notes and the hand notes also to the Canva. And
Great.
when I am due to give the question, sir, Majumdar
Yes, sir.
sir,
Yes, sir.
when should I give the questions?
Uh,
The quiz?
After the information science, sir.
Okay, there is some time. Okay.
Right, sir. Because next week, because we are having very less schedule, so we'll club next 5 modules. Then we'll combine for the quiz too.
Okay, great.
Right.
Okay,
So thanks everyone once again. Let's meet on 3rd October. Thank you everyone. See you on 3rd October.
Okay, great day.
Diksha, Nitya, kindly close all the sessions and the recordings.